So I will start with my part for the 2-day training parallel programming day. In my part, I will follow the GPU programming from Christian by talking about how to do GPU programming with OpenMP Offloading. And my name is Xin Wu. I'm working at Paderborn University, Paderborn Center for Parallel Computing. So before we start, and also as a short buffer for the participants who just joined, first I would like to introduce Institute Paderborn Center for Parallel Computing PC2. We are a research institute at Paderborn University and also a member of NHR Center in Germany, Nationales Hochleistungsrechnen. And also we are a member of HPC NRW. So what do we do at PC Squared? So first, we provide HPC infrastructure and services to our users around Germany. So as you can see on the right side, currently we have two systems. Our flagship system, Autos, yes, you are using Autos for this course, was built last year. It has more than 140,000 CPU AMD Gen 5 CPU cores, and also more than 100 NVIDIA H100 GPUs. So for this course, you are using those, let's say, the state-of-the-art GPUs to do the training so that you can really feel the computational power from GPU. So we have a second system. This system is Noctua 2, which was built in 2022. It has more than 140,000 AMD CPU cores and also more than 130 NVIDIA A100 GPUs. So those are the HPC infrastructures we provide to all the users in Germany working at German universities. And besides providing HPC infrastructure, we also do our own scientific research and development in many research fields. So for example, novel method development for using HPC system to do heterogeneous computing or reconfigurable computing, and last but not least, doing some development for emerging and next generation computer architectures. And last but not least, we also provide HPC training for our users and also users around Germany so that we can benefit the most from the HPC system. And then a slightly information about me. I started GPU programming in 2008, yes, roughly, let's say, almost 20 years ago. And I did my PhD thesis at Max Planck Institute für Kohlenforschung about quantum chemistry using GPU. And at that time, I wrote a book chapter published by John Willey about how to do quantum chemistry or electronic structure calculation by using graphic processing unit. And currently, I'm a scientific advisor for theoretical physics and chemistry at PC2. And for teaching, I'm doing GPU programming in OpenMP and Julia. And for doing research, I'm using another accelerator, the so-called field programmable gate array to accelerate quantum chemistry calculations. Okay, let's start with the real GPU programming with OpenMP offloading. So this is a general overview about the agenda for this afternoon. So this lecture will take roughly 60 minutes. I will give you a short introduction about why to use OpenMP to program GPU to give you motivation about it. And then it will follow a very simple but very interesting Hello World program from GPU. And then I will talk about more how you can maximize the utilization of the GPU parallelization by using OpenMP. And then it will followed by two examples. So learning by doing, I will give you two simple but very practical examples how to write your OpenMP GPU offloading program without modifying the CPU code. Yeah, that's the magic. And then a short summary. And afterwards, we have a 20 minutes break. And after 20 minutes break, we have the hands-on part. For the hands-on, we prepared, let's say, 3 tasks. And the time for those tasks is 15 minutes plus 15 minutes. So for the first 15 minutes, you can dive into the exercises, reading it, trying it quietly. And then I will take another 15 minutes to show the result so that you can benefit the most from the exercises. And in the very end of this exercises, we have an open task, open-ended task. And if you found it interesting, and then we can continue our discussion even after the hands-on part. So let's continue with introduction. This slide shows you the top 5 HPC system currently in the world. It was published in the end of last year, 2025. As you can see, now we are in an era of the so-called GPU computing. The first 2 HPC systems located in the United States are equipped with AMD GPUs. And then the third one uses Intel GPUs. And the fourth one is from Germany, Jupiter from Forschungszentrum Jülich, use NVIDIA GPUs. And the last one, the fifth one from Microsoft is also using NVIDIA GPUs. As you can see, this is a, let's say, a zoom of many different GPU vendors or GPU types and so on. And for those zoom, you have different vendors, different terminologies, and different programming models, and different software stacks, and so on and so forth. As you can see, this is a real chaos. And also, it is a nightmare for, let's say, software development and maintenance, because there are so many different ways to program GPU. You can use, for example, OpenMP. You can use OpenCL from the early days, or using, let's say, the NVIDIA own way, CUDA, or use HIP from AMD, or use DPC++ from Intel. So it's not really convenient to utilize, to write your code once, and then to utilize the GPU power from different vendors. That is why a portable solution is needed, because we want to write our code once and then benefit the most from our development, right? We do not want to rewrite our code for this GPU, for that GPU. That is not an interesting work. And a portable solution is right here. You can see OpenMP programming. It provides you a portable solution to just write your code once based on the CPU code, and then this GPU code can run on all the GPU devices from different vendors. Okay, this slide shows you a very high-level illustration about what is GPU offloading. Let's say here you have your program code, like a very large book. You have GPU code, you have your CPU code there, and those CPU code, without any question, runs on those CPU processors or the CPU cores. And one may have multiple CPU processors or multiple CPU sockets. Together, those are called the so-called host system. And GPU offloading means for your CPU code, you have some computational intensive functions. You just convert those CPU code and then to offload those CPU code to the GPUs. This is very simple, right? Just convert the CPU code doing some, let's say, magic compiler, very smart magic compiler conversions, and then your code can run on GPU without any problem. And to be more precise, for OpenMP GPU offloading, they use the word target device to denote the GPU, because for OpenMP offloading, it treats all the processors, all the accelerators as target device, because in the future, there may be more fantastic accelerators other than GPU. That is why it has a very independent name called target device. And OpenMP GPU offloading is available from OpenMP 4.0. It has been for 6 years or 7 years. If I remember well, OpenMP 4.0 was released in 2018 or 2019. And by using OpenMP offloading, you can do this for C code, C++ code, and of course, Fortran code. And this is a high-level GPU programming by using OpenMP directives and API functions. I think you have learned some useful OpenMP directives and API functions on the first day. Now you can, let's say, reuse those knowledge and then apply this knowledge or similar knowledge to GPU, which is very, very easy and convenient. So for the hardware, the GPUs are called the target device. So there's no vendor specific for GPU. It is just called a target device and can be applied for any GPUs from different vendors. And for you as a developer, you only need to write one version of the source code, and then you can compile it and then run it on different graphic card from AMD, from Intel, from NVIDIA. And another good news is for the compilers, there are rich compilers you can use. For example, from NVIDIA HPC SDK or AMD ROCm or Intel One API, or you can use, let's say, open free and open source compiler, GCC, Clone, and so on. There are multiple choices. So you have the freedom to make your own choice, not bounded by one compiler for your development. And also for the so-called target device, as I have repeated many times, you can run your code on NVIDIA GPU, AMD GPU, and Intel GPUs. So let's say if you write your GPU code by using OpenMP offloading, you are writing the so-called high-level GPU programming. But here, I would like to emphasize that high-level GPU programming does not equal to low performance, right? In this course, I'm going to show you that even writing your code at very high level GPU programming, you can achieve very high performance, even beat the performance that can be provided by CUDA. Yes, this is true. And the key thing is you can utilize millions of GPU threads that is available there, and then to take advantage of the so-called massive parallelization. I'm going to dive into this so-called massive parallelization in the next session. And here I'm just show you the, let's say, show you the case. To make this even stronger, here is a published paper at the Supercomputing Conference 2 years ago, SC 2024. As you can see, there is a group of developers. They try to take advantage of the performance portability for calculating electron repulsion integrals, very important calculation in quantum chemistry, by using OpenMP to do the acceleration. And it turns that the code based on the so-called CPU kernel can run on NVIDIA GPUs, can run on AMD GPUs, can run on Intel GPUs. So you just, based on your CPU code, write it once, and then it runs basically everywhere. This sounds amazing and sounds too good to be true, but I will show you this is realistic. So before we continue, this morning, Christian has talked about the CPU and GPU architectures. Here I will, let's say, recap this very quickly. So for the CPU architecture, you have many cores, let's say, normally less than 200 CPU cores. So usually you can have, let's say, several hundreds, or maybe 200 or 300, I'm not sure, but around the level of hundreds threads per CPU. But normally with those large number of threads, you know, goes beyond the number of the CPU cores, available CPU cores. Normally you do not have a better performance gain because those threads may compete with each other and then even lower the performance. On the other hand, let's focus on the red words here. If you are using GPU, the key to have a good performance is to launch tens of millions threads, yeah, which is a really massive number of threads to take the computational power from all those CUDA cores or SMX, you know, those CPU processing unit, GPU processing units. Here is a, let's say, a detailed comparison for CPU and GPU. Let's look at the performance. As you can see, for CPU and GPU, you know, roughly appear on the market the same year. The GPU wins for the theoretical performance, you know, peak performance, and also GPU wins for the memory bandwidth, and GPU consumes slightly more energy. But in the end, if you calculate the performance per watt, GPU wins clearly. For A100 GPU, it can provide 2.7 more energy efficiency or power efficiency than the CPU. Yeah, this is a very important topic nowadays because HPC centers consumes a lot of energy. So it is very interesting and practically useful to save the energy to do more calculations. And last slide about introduction is, you may ask me, okay, now I have an application. Could you please tell me which kinds of applications is suitable for GPU? So in general, the application should have regular patterns and fewer random access to the memory, and also minimal conditional jumps. So to be more precise, there are some typical examples. For example, image or video processing, like you can see here, the image filter applied to the X building of PC2 to do the image processing. This is a suitable application for GPU. And also linear algebra applications. And last but not least, nowadays AI, machine learning, deep learning applications, those are also suitable for GPUs. And in reality, for the so-called measured speed up, it's somehow highly depends on the capabilities of the programmer for GPU. That is why we have this course for you, so that we hope by after this course, you can be a very capable GPU programmer and then apply the techniques that you learn here to your own research project. So hello world from GPU. Okay, this is a very short but complete code that fits on the slide. So hello world for the GPU, let's look at the source code. So before we start, we need to include this OpenMP header file, as you have learned on the first day. And then you create a variable which stores the number of the target device, and then use the OpenMP API function, OMP get number of devices, very intuitive. And then you know how many target devices, AKA GPUs, available for your calculation. And then you start the so-called target region or OpenMP target offloading region. This is something new for this course. What does it mean? If you look at the right side of this slide, you see I'm showing you the OpenMP target directive. Simply create the so-called target region and then to offload your calculations to GPU. That's it. You see, very simple, just one directive, and then you are using GPU. And then inside this OpenMP target region, you can query, okay, if this device is an initial device means, the starting device. The starting device is, of course, CPU. So if this is a CPU, and then you will see hello world from CPU. Otherwise, you will see, okay, great, now I'm using GPU. Hello world from target device or GPU. So as you can see, it's very compact, very simple, just I'm not sure, maybe 5 lines of code based on your original CPU code. Now your code can run on GPU without any problem. And a complete example is here. You can find it from example folder 01 hello GPU. As you can see, now we need to manage, let's say, our devices, the so-called device management. For this, you can simply use OpenMP API functions. Here is a list of those functions. So first, you can query if this is an GPU device. So, or if this is an initial device. As I said before, an initial device is a host device. A host device is CPU. So this gives you the number 1 if this function is called from the host device. Otherwise, it returns 0 because this is called from the target device. And then you can get the host device number, for your calculation, for your device management, and as well as the number of the target device. For example, GPU, you can get how many GPUs do I have for this calculation. And last but not least, you have full freedom to choose or to pick which GPU device would you like to use for your calculation by using OpenMP Set default device. And the number of the default device is counting from 0 to the OpenMP get number of the device, you know, the maximum. So it's very convenient to use. And if you would like to try it out, here is a very brief instruction how to do it in using Slurm on the Autos cluster. You need to put a GPU partition there, and then load the modules, and then compile by using NVC for C code or NVC++ for C++ code, like what you have done in the morning. The only one change you need to do here is to specify -MP means OpenMP, you know, an option for OpenMP. And then for this option, now you are using target even equals GPU. So very simple, just use the NVC or NVC++ compiler and indicate now I want to run OpenMP and target on the GPU. And then you have your GPU offloading code. And if you run the code, you will see that, for example, on one compute node, there are 4 GPU devices available, and then the GPUs are NVIDIA H100. And if we continue, or maybe this morning, Christian has talked about the GPU memory or CPU memory, etc. So because for OpenMP, the standard does not restrict to a specific target device, which means this target device can be GPU, can be FPGAs. Yes, really. There are some experiments to offload GPU to offload calculation to also to FPGAs. And for the memory system, it is supported by the so-called mapping. You can map variables which can be a scalar or a vector, or for example, array between the host device and target device. And in order to make this very portable, there's no, let's say, limitations for the physical architecture of the memory. So this memory can be shared for the host device and target device, or the host device and target device has their own memory. The so-called, the memory is distributed. There's, you as a programmer, you needn't to worry about it too much. You just need to do the so-called mapping, and then the OpenMP implementation will do the optimal choice, either sharing the data or copy the data for you automatically. So this makes the life of the programmer or your development much easier. Now we just assume GPU as a target device and assume the most common setup. Let's say the host device is a CPU with its own memory, and the target device is GPU with own memory, and then connected by PCI Express. So to do the memory management, you can either use OpenMP runtime functions or to use OpenMP compiler directives. So there are multiple ways to do this. I will give you instructions for both, and you have the freedom to pick which would you like. But before we move on, before we dive into the details, here is a short tip for the performance consideration. Here, for example, if you are using NVIDIA H100 GPU, and then the GPU memory bandwidth is, let's say, super high, it's roughly 2,500 gigabytes per second. And the connection between host and target device is only 64 gigabytes per second. This is, let's say, roughly 3% of the GPU memory. So performance tip, if you want to have higher performance, it's better to avoid unnecessary data transfer between host and target device, because this is really slow, as you can see, the PCI Express. Here is a photo showing you what is a real PCI Express. So to avoid the data transfer between host and device as much as possible, if you want to have a performant GPU code. So for the memory management using OpenMP runtime function, there's only 3 runtime functions. The first one is to allocate memory, very common or very similar to what you do by using malloc, memory allocation on CPU. And then memory copy. This is also very similar to memory copy, this common C function mem copy. And last, free function to free the memory. And as you can see, those 3 functions are slightly longer because you can also specify the device number. So you can pick which device you would like to use, which device you would like to allocate the memory, and so on and so forth. But in principle, those 3 functions are very simple and easy to use because they are basically very similar, or let's say the same as malloc and memory copy and free for the traditional C or C++ functions. And if you do not want to use those OpenMP API functions, you can still choose the so-called OpenMP compiler directives. For this purpose, you only need to specify, remember we talked about mapping. You need the clause map to map a variable. This variable can be a scalar or an array between CPU and GPU. So the syntax for map is also very simple. You put map here. And then for this mapping, you have several choices. The first one is to always do the mapping. So this means always do the data management or data transfer between the CPU, the host device, and the target device. And then for the map types, there are several options for you. The default one is the to and from. This means you will transfer the data from the host to the target device, and also after calculation to transfer the result back to the host again. So this is like you can see here, do the copy before doing the calculation, and then copy it back again to get the result. And also you can specify allocate without doing explicit copy, or you can only do this to map type, which means only copy the data from host to target device, or only do from to copy the final result from target device to the host. And last, you can specify a list of variables you would like to do the copy. You can copy, you can map a scalar, and it's very simple, just put map scalar and then it's done. You can also map an array. So for mapping an array, you need to specify the base of the array and then the offset for this array and then the length. Because I know there are some C or Fortran compilers out there. To make this point more clearly, here is a more concrete example for C. So let's say you have a vector which contains 8 elements on the CPU. So to map, you write it here, map vector starting from 1 with a length of 4, this means you will copy actually from the second element, because C is zero-based indexing. So here, copy from the second element, and then with the length of 4 elements from CPU, the host, to the target device. Yeah, sometimes these small things can be confusing for C and Fortran programmers. So just to make it more clear here. And then we have done our code offloading, and you can try this to put it in your CPU code, very simple target, put it into the target region, and then map to transfer the data from CPU, between CPU and GPU. Yes, the development is done, but you may notice that there's no acceleration at all, because this code with only 2 words from OpenMP, this code hasn't taken advantage of the GPU parallelization. That is why we are going to talk about parallelization on GPU very shortly, so that you can benefit and learn how to take advantage of GPU acceleration. Because OpenMP uses this host-centric execution model, which means the host starts the so-called initial device and then do the offloading. And then this initial thread does not execute the target region, let's say, directly. And in the end, as you can see here, with the red font, only 1 GPU thread. And here on the right, you can see this image very clearly. Only 1 GPU thread does the computation. That is not good, because there's no parallelization at all. So in order to get the so-called massive GPU threads, you need to apply OpenMP parallel worksharing construct into your code. I'm going to talk about the parallelism on GPU, let's say from higher level or more theoretically. So there are 3 levels for GPU parallelization. The first level is the so-called single instruction multiple threads. This is somehow similar to the CPU SIMD vectorization. So one single GPU instruction can be simultaneously executed by a group of 32 threads. This is the so-called warp in terms of the CUDA term. And the purpose for this is to have high parallel efficiency at the instruction level. Very low level, but highly efficient, like CPU, SIMD on CPU. The next level of parallelization is GPU threads. So a GPU can have multiple warps, and then those warps are grouped together to have up to 1024 threads. This is the so-called GPU threads. And for CPU, you have also learned CPU multi-threading with OpenMP, and those are somehow also rather similar. But the very last level of parallelization, the so-called grid level parallelization of GPU threads, is not available for CPU. The reason is the architecture differences and the focus of the, let's say, processor design. This level, you can have, instead of one group of 1,000 threads, you can have multiple group of, let's say, 1,024 threads. And then you will have millions of threads. And this is the secret why GPU can achieve high parallelization and give you very high performance. This slide is maybe somehow challenging for you to fully understand the working mechanism. But the key message here is because of the third level parallelization, GPU can reach very high throughput by hiding the memory access latency. As you can see, the scheduler may call different blocks to run the calculation. And meanwhile, if a block needs some data from GPU memory, the scheduler can switch the GPU blocks very fast, and then to make the ALU arithmetic logic unit to always busy, and then to achieve very, very massively parallelization. Yes, that is a secret for GPU parallelism. Those parts may be slightly theoretical, but no worries if you still have some questions. You needn't to have very deep knowledge to have very performant GPU offloading code if you are using OpenMP offloading. So how to put all three levels of parallelization into your OpenMP offloading GPU code? You can simply add parallel for SIMD, only 3 words, and then you have 2 levels of parallelization on GPU. Yes, it's very simple. Parallel for SIMD, and then you already have 2 levels of parallelization. As you can see here, you already have multiple threads, much more than the threads shown here. You have 1,000 threads, yes. And then for those threads, you have similar API functions from OpenMP, like what you have learned on the first day. For example, set the number of the threads, get the number of the threads, get the thread number, and so on. So those are very similar, and those similarities lowers your, let's say, learning curve for using OpenMP by doing GPU development. However, by only using 2 levels of parallelization, GPU is highly underutilized. Why? If you look at the figure on the right, you may see that from, let's say, this very abstract image, you only have 1 team of threads, and only 1 streaming multiprocessor is busy for the GPU. And this is not good for the performance. You will have lower performance. And our next goal is to saturate the entire GPU processors as much as possible. So to do that, you only need 2 words. The first word is team. Okay, you want to have a team of GPU threads, not only one team, but multiple teams. Multiple teams to do the calculation. And the second word is distribute. You need to distribute the workload. And then that's it. Now you have 3 levels of parallelization, and then you can take all the parallelization capabilities to use GPU parallelization. And to make this description more vivid, you can look at the image on the right side. You have a target device. And for this target device, you have, let's say, a massive number of teams, GPU threads to do the calculation. And those calculations are executed by the so-called out-of-order execution. And this is very important because out-of-order execution may, let's say, may sometimes, to give you some incorrect result. So we need to keep this in mind, and also no synchronization for this out-of-order execution. So that is why for the very last example, I will show you how to control this and give you the correct result for your code. Okay, I think this is a key takeaway. And for this course, maybe you can print only this slide. So, so far, we learned how to use OpenMP to do GPU offloading or target device offloading, we only need, let's say, 4 kinds of keywords as directive from OpenMP. The first one is target to do GPU offloading. The second is teams, distribute, which will distribute your calculation to many teams. It is the so-called a league of teams, many teams to do the work. And for each team, you do the threat level parallelization, the normal or the traditional parallel 4. And last but not least, you also take advantage of the SIMD vectorization on the GPU. So the most convenient way or the most clean syntax is summarized here. Target and then map, transfer the data, and then teams distribute parallel 4 SIMD, and then that's it. This is the core takeaway from this course. By using those, simple syntax, you can turn your CPU code into a powerful and performant GPU code within, 1 minute or even less. To demonstrate to you the power of OpenMP GPU computing, I will take the rest of the time to go through 2 examples to show you the performance. The first one is about how to compute the Mandelbrot set. A Mandelbrot set is a set of complex numbers, C. So just by repeat this iteration starting from Z0 equals 0, and then to do iterations if this iteration does not converge, and then we can use the number of the iterations to color an image. And then on the right side, you will see this final image. Let's begin with very briefly with CPU implementation. So the first CPU implementation, you need to compute 1 pixel. So to calculate it, it is very simple, just to do the repeat. Here in this example, we have a repeat of roughly 32,000, which is large enough so that we have enough workload. And then to check if this converges, if it does not converge, it will, let's say, break the loop, and then to move on to the next pixel. The pseudocode for computing 1 pixel is shown here, and the entire source code is also available in the example so that you can, let's say, you can try it out during the hands-on session so that you get more feeling about the calculation. And then for CPU parallelization, you need to distribute the work, for example, to calculate 1 column, as you can see here, 1 column, and then continue to use another loop to go through all the columns to calculate the image. And before we continue, here is a short quiz for you so that maybe you can think about if we are using CPU multi-threading, CPU parallel 4 multi-threading, which you have learned on the first day, which loop should we parallelize? To parallelize 1 pixel or 1 column, or to parallelize the calculation of the image, because there are 3 levels of for loops. Feel free to turn on your microphone to, to just response, or also type in the chat. I can also see your result. So which loop would you like to? Okay, yeah, thanks, Matthias, inner loop. Okay, yeah, thank you very much for your feedback. So I think Matthias means to compute the image, which is exactly. And yes, let's forget about the let's say, computer code. Let's look at the image on the right side. So our purpose is to compute the entire image. For CPU parallelization, we can distribute each column or several columns to a CPU thread, as you can see here, with multiple CPU threads. And then we can do the parallelization. And a key for you to take away is to have a reasonable number of threads. Reasonable means do not start millions of threads, right? On CPU, if you start millions of threads, yeah, I'm pretty sure that you know, the CPU will be overheated. Yeah, this is not to do that. Start with I don't know, several tens of threads, or you know, similar to the CPU, the number of the CPU cores. And here is a small performance report. For serial code, one need to use, let's say, about 11 minutes. You know, it's a quite long time to do the benchmark. And with 96 cores, you achieved, you can finish the calculation with within 7 seconds, and you achieved a speed up of 89, let's say 90 times faster. This is not as perfect as 96 cores because of possible reduced clock frequency if all the CPU cores are using. But anyway, as you can see, this is not a bad parallel efficiency. We achieved roughly 90 times faster with 96 CPU cores. And this is a slightly, let's say, performance model analysis. I'd like to skip this slide, but the key takeaway for you is this calculation is compute bound, point 1. Point 2, this computation is therefore very very suitable for GPU architecture. So it's compute bound, it's suitable application for GPU. So to port it on GPU, here is our first try. You know, our first try is always starting from naive implementation. For naive implementation, you needn't to think about what to do. You just copy paste the previous OpenMP directives to your CPU code and then run it. It's very simple. But anyway, I would like to explain this very quickly. Target to do GPU offloading. Map only use from because in the beginning, there's no data need to be transferred to the target device. And then last, copy the data image from GPU back to the host. And then we have 3 levels of parallelization on GPU. We take advantage of GPU. And then if we compare the performance, we use the entire CPU socket, you know, one CPU socket as a baseline. It's 7 seconds. And this naive implementation already gives us some speed up. Not fantastic, but we have some speed up, 1.3 on the GPU. But as I mentioned, on the GPU, in order to have massive parallelization, current naive implementation only parallelize the column loops, right? Here is, let's say, on the right side, you see a very similar graph, but this graph is for GPU threads, very similar to the CPU one, but this gives you the, let's say, illustration how this naive implementation works. For this naive implementation, one only utilize, let's say, 8,000 GPU threads. This sounds a lot. Yes, I fully understand. This sounds a lot. 8,000 threads, this sounds a lot. But keep in mind, for good performance on GPU, we need a reasonable number of threads. In this content, I mean, if we talk about reasonable number of threads on GPU, we talk about millions. We talk about tens of millions. So 8,000 GPU threads, I would like to say it's nothing. It's too small. So in order to maximize the parallelization, we need to launch more and more GPU threads. So the basic idea is...
Can I ask a question?
Yes, please.
Where do the 8,000 comes from? Can you read out these 8,192 somewhere? Is there some output where the GPU reports, oh, this is the number of threads that were working?
Yes, this is a very nice question. For this example, we are using, let's say, 8,000 times 8,000 pixel for the calculation. So that is why here this is 8,000. And you can really get the number of the GPU threads running by using OpenMP API functions. Remember, yeah, this is why I really like OpenMP. You can, for OpenMP GPU offloading, you can easily use OpenMP, get number of the threads, and so on, to get more detailed information about your GPU threads. This is very convenient. Yeah.
Thank you.
Yeah, you are welcome. Because of the time reasons, yes, for this particular example, we are using 8,000, let's say just 8,000 times 8,000, image. So that is why here we only have, let's say, roughly 8,000 GPU threads. So the key message is here to start massive GPU threads. As you can see here, yes, this image shows you a couple of GPU threads, but here you know what I mean to start 8,000 times 8,000 threads and let each GPU thread to compute each pixel. This is the so-called, let's say, massive parallelization. And because for the calculation, we have a perfectly nested column and row loop. As you can see, basically here, it's a square. And then we can, and also the computation of each pixel is independent. We can manually linearize the nested loop and then create 67 million GPU threads. Yes, I read it again, 67 million GPU threads. This sounds insane, for CPU, but this is the key for the performance on GPU. One needs millions of threads, tens of millions of threads. And then each GPU thread just compute one pixel. For this one, you need to change, let's say, 3 lines of your code. The first line is the for loop to make it linearize. As you can see, the linearize, and then to calculate the index of the column, and then to calculate the index of the row. The full example is here so that you can play with it. And then you will see, oh my goodness, this is the so-called speed up, right? After the linearization of the loop, the calculation time reduced from 5 seconds to about 0.1 second. This is, let's say, a really significant speed up. If we compare the performance of one CPU socket and the GPU, you have, let's say, roughly 40 times faster. But one thing that I do not like is to change my CPU code in order to let it run on the GPU. Because the promise from OpenMP GPU offloading is one should never make any changes for the CPU code. Is there an more suitable, more easier solution? Yes, there is a solution that you needn't to change your code by a single letter. You just use claps in the OpenMP GPU offloading, and then claps will merge the nested loops automatically. In this way, you can still keep your CPU code as what it looks like, and then only add claps 2, which means the compiler will linearize the loops automatically for you. And then you have the automatically collapse or automatically linearized loop. This runs 0.192 seconds, which is, I'm not sure, slightly slower than the manual linearized loop. But frankly speaking, I think this very, very small, tiny time may change, for different measurement or for different number of pixels. So in my opinion, by using claps is more convenient and give you very high speed up. And some of you may think about how about the performance compared with CUDA code or some, dedicated, highly optimized code. Here we have a CUDA code which runs slightly, let's say, again, slightly slower than the OpenMP GPU offloading code. But I'd like to say those 3 kinds of code, they have roughly very similar performance. So the key message that you can take away from OpenMP GPU offloading is, first, you are able to do GPU programming at high level and very productive without changing any CPU code. Yeah, it's possible. And second, the GPU code will be performant without sacrificing any computational performance. This is the magic and the most attractive point that you can have. If you do not trust me, yes, you can try this example 02 Mandelbrot, and then you can play with it and find out the magic there. So our very last example, because of the time reason, I will go through this very quickly to calculate pi by numerical integration. Without repeat, the basic algorithm about how to calculate pi, you can divide the integration into small intervals and then sum it up. And you can have this implementation on CPU. And for this calculation, it's compute bound, but it has a risk condition. This risk condition also exists on CPU because this is the underlying algorithm. For CPU, you need to use this reduction plus P, and then the problem is solved. And here is a very simple CPU, let's say, code for doing numerical integration to calculate pi. To do this on the GPU, you also need to pay attention to the data race. And in order to solve this data race, unlike using CUDA or some other programming language, you need to write lots of code. For OpenMP offloading, you can use the identical reduction as what you have done by using OpenMP for CPU, namely reduction. And then you solve the problem. Underlying this reduction, there are 2 levels of reduction. One is within the, let's say, the GPU threads, the group of the threads. One is among many different teams. But, as a programmer, as a developer, or doing your research, you needn't to care about those details, underlying details. You only need this single reduction, and then with other normal, let's say, GPU offloading directives, you can run this entirely on GPU. you know, I'm a performance guy doing performance optimization and parallelization. I would like to compare the performance. So for the serial code, for this calculation, let's say with lots of intervals, it may run 20 seconds. And the same code parallelized on CPU as what you have learned on the first day from Matthias' lecture, it can run, let's say 0.2 seconds, gives you 93 times speed up, which is pretty nice, you know, 96 cores, 93 speed up, which is pretty nice already. And if you want to do it, run this with few lines of OpenMP GPU offloading and directives, you achieve 0.074. Yes, 0.074 second, which gives you about 278 times speed up, which is amazing. And the most amazing part is you didn't change the CPU code. The CPU code is the same, never changed. And you only changed, I don't know, maybe 10 OpenMP directive words. And then you have 200 times faster. This is insane, let's say. So I would like to repeat this again, a little bit wordy person. So by using OpenMP GPU offloading, you have productive high-level programming on GPU. And at the same time, you also have very high computational performance. So high level does not equal to lower performance. Yeah, to be more productive for your research, to keep it high level, and at the same time, you have significant speed up. Here is the full compute code. You can find it there. And I think this is the end of this session. And before we close, I would like to summarize the most important takeaways from this session so that you have an overview. First, OpenMP support offloading the most expensive computation to the target device. So here, as you can see here, in this course, we are using GPU. And after this introduction part, we talk about the GPU architecture. And the key takeaway is to start massive parallelization with, let's say, millions of GPU threads or tens of millions of GPU threads. This is the key, so that you can have all the three levels of parallelization on GPU. And then you only need a few OpenMP words, let's say, OpenMP directives, and then you can reach very high performance. And last but not least, for some suitable applications, maybe for your own research, you can get significant speed up if your own research domain is, let's say, compute bound or lots of calculations over there, and then you can benefit from this immediately with only a few words. I think that's all for my talk. Slightly, slower than the plan. And yes, thank you very much for your attention. Hello, everyone. I think after a short coffee break, you feel refreshed. So before we start with the hands-on exercises, in the chat, Gregor asked a very interesting question. I think this question may be very interesting for many developers who want to maximize the performance of their code, both on CPU and GPU. And this is doable by using OpenMP. Maybe I scroll back to the slide I would like to talk about. Yes, this is the slide. I would like to discuss this very briefly. So for OpenMP offloading, you specify the so-called target region by using target, and then you offload the calculation from CPU to GPU. And then, as mentioned in the question from Gregor, and the I/O part, the heavy part to do I/O, can still be done or run on CPU. You can let the CPU thread, which has offloaded the work, to do something useful instead of waiting there or being suspended and so on, and to do something, to do some work, to do some computation, so that in the end, those different calculations or operations can do simultaneously, so that your overall performance of your application can be maximized. This is doable. I think the directive from OpenMP is no wait, if I remember clearly, which means do not let the CPU initial thread to wait for the GPU work. Very easy to understand, intuitive, no wait, and then just continue with some I/O work. This is fully portable. I'm not sure if I answered this question in the chat, if everything is clear. Okay, great, thanks. So as our plan, so let's have 15 minutes. Yeah, I will type it in the chat. Let's say at 14:40. Yeah, I take a look, and then take a look the Hanzang, and then without interruption, and afterwards I will clarify this again. Hello, everyone. Yes, I hope you have enough time to, let's say, to dive into the very first task, query the target device by using OpenMP. So now I'm going to, let's say, do some live demo so that you can take a look, and let's learn together about how to use OpenMP to query the target device. I think the first two tasks are straightforward. You can create a Slurm job script and then submit the job. And then the key question is here, the error message. Oops. The key problem is here. The error message will appear, and then we need to identify and fix the error. So let's say I think you are all on the autos, and yes, to do the exercises, you can copy the let's say the entire directory to a directory that you would like to have a name, and then to go to the exercises part, and then go to 0, 1. So here you can see several codes, and here this code accelerator query .c. This is the original one with problems. You can open this, and then here you see our intention is to get the number of the so-called accelerators as known as GPUs, and here we start a target region, and we want to have the number of the accelerators and so on. So everything looks normal, looks pretty fine. Here we get a number of accelerators. You know, this OpenMP get number of devices is also correct, like many other OpenMP function calls. And then we print the number of the accelerators. If this number is 0, no accelerator found will be printed. Otherwise, to print detailed information about the accelerator, as you can see. So basically, this code is short and very concise. So if we submit this code, we get our result, which is this one. We will see that hello world from GPU. Okay, this is totally fine as our expectation, but no accelerator found. This is not inconsistent with our expectation. So the key is for some OpenMP API function calls, it may behave differently inside of the target region and outside of the target region. So if, as I mentioned before, let me switch to the slides very quickly. Yes, here, as you can see, for example, this is initial device. If this API function is called from host, it gives you 1. Otherwise, it gives you 0. And if this number of the device is called, it returns the numbers of the target devices. And this is only valid outside of the target region. So which means this function can only be called from CPU. So unlike OpenMP for CPU, so for the API functions, it has the same meaning, you know, works always the same because there's only one host, one CPU as a device. For this heterogeneous system, some of the OpenMP API function calls may behave differently. And the behavior is determined whether this function is called from host or from the target device or the device region or the target region. So for this OpenMP get number of the devices, this must be called outside of the target region. So which means only the host can give you a valid result to call this function. Therefore, to make it correct, you can simply, let's say, move this line out of the target region So now the host, namely the CPU, will call and to find it out the number of the devices and then get the number here. And then in the target region, the Euro business, hello world from host or hello world from GPU, and then print it out. So this the key message that you can take away is some OpenMP API functions for offloading may behave differently depending on the host or the target device. So this is some, let's say, common mistake that you may encounter. I think I have the same version for those two. Yeah, those two are the same. Yes, those are the same, except here. So let's submit. Maybe you can also run this job so that this job runs very fast, I think. Now it's done. So let's look at the very last. As you can see, now you have one accelerators found because in the Slurm job script, the Slurm job script only requests one GPU, one H100. That is why here you only see one H100. And then the so-called compute capability, basically this is how the GPU is capable, defined by different capabilities. And then the GPU clock frequency, number of streaming multiprocessors, and the core for each streaming processors, and number of CUDA cores, global memory, and shared memory, and register, and so on and so forth. So those are the, let's say, hardware specification for this GPU device. And a good news, if you are using OpenMP GPU offloading, you can ignore all those or almost all those hardware specifications, because OpenMP abstract away the details and let the compiler developers to pick the optimized software settings for the number of threads and so on for your application more or less automatically, so that you needn't to, let's say, think about too much about those hardware details in order to have high performance. That is, let's say, very attractive, because for most domain scientists, they want to focus on their algorithm or focus on their application instead of the global memory, for example, or the number of CUDA cores and so on. So this OpenMP GPU offloading abstracts away those different hardware details, and meanwhile can also provide you high performance. So this is the benefit for using this. And yeah, I think I finished the first task. Yeah, those are the hardware details, but those hardware details are not really, let's say, critical if you are using OpenMP GPU offloading, because OpenMP GPU offloading can abstract those away so that you can focus on your domain science or your application and so on. So is there any questions for task 1? Or is everything clear? Okay, great. Thank you for your feedback, Matthias. And yeah, and also thank you for your feedback, Julian. And Yeah, thank you very much. Yeah, it's a very intensive course, 2 days. Yeah, I'm really happy that you stay with us for such an intensive course. So without any delay, maybe you can try the second task for again 15 minutes. This is let's give it to 15. I will write it in the chat. Give it to 15 o'clock. Yeah, and also if you need fresh air, take a short break and take a look at the task 2. And from 15 o'clock, I will clarify the task 2 so that we can learn together. If you have any questions, feel free to ask. Either turn on your microphone or write it in the chat. I will monitor both. Okay. Hello, everyone. Yes. I think the task 2 is somehow short, but this is very important if one try to use OpenMP offloading to do the GPU programming, because this has important implication for the performance. Before we dive into this exercises, I would like to to call your attention to this memory management again for the host device and the target device. So for the GPU, let's say most of GPU H100, the GPU memory bandwidth is high, but the bottleneck is PCI Express. So as I mentioned, for the best performance, one should try to avoid unnecessary data transfer between host device and the target device. And for the memory management, you can use 3 very similar functions like malloc or memory copy and free, like ordinary C functions. By OpenMP, you just prefix OMP target and then to do the similar functionalities. And for those functions, you only need to provide an additional parameter or maybe 2 parameters for the destination device or the source device. Can be host device or target device, to do the data transfer. So those are the basics for task 2. And for task 2, I think the first 2 tasks are very simple. Just run the Slurm job again. And the key is here. You need to measure the data transfer rate and then put the, let's say, transfer rate here and to see the differences. For the source code, it's slightly longer this time, but anyway, I would like to talk about it shortly. So for in the comment, you see H2H source is host, destination is host. So this H2H means, let's say, data transfer or data copy only for the CPU memory, like normal mem copy for C code. And H2A source is host, and destination is accelerator or the target device. For OpenMP, there's no one specific device. You can just call this accelerator or target device. So basically, for this data transfer, it needs to go through the PCI Express. And the last one, A to A, is source from accelerator, and the device is also accelerator. So basically, the data transfer takes place only for the accelerator. And then you can search the OpenMP target function call. This looks a lot, but basically just locate memory and then do memory copy, as you can see here, but with the device number. Device number means, for example, here, as you can see, H to H is CPU to CPU. So here you just get the number of the for the CPU device, which is obtained from the previous one, the OpenMP get initial device. So this OpenMP get or OpenMP set, those API functions, those are very convenient to use, in my opinion. Here you just get the host device and do the memory copy. Here I run it twice because the first one is warm up and the second one is a measurement. And this is the same for the CPU, GPU data transfer, through the PCI Express. And the last is between the target device, between the target devices, let's say between GPUs, and then to measure the transfer time, and then to print out the bandwidth, and then to release the memory. As usual, you call this free, this CPU function free. Here you call OpenMP target free. I hope now the high-level structure of this short code is clear to you. So we run the data transfer rate measurement for CPU and CPU and CPU and GPU through PCI Express, and lastly, GPU and GPU. And now we can submit the job like as batch run job. And yes, I created those calculations intentionally to keep it short, so that for some of you who are not who are impatient, you can get the result immediately. So now the most interesting part, as you can see, the host and host data transfer is like 44 gigabyte per second. This is low. And by the way, this is not a very professional memory bandwidth measurement like what was done by Matthias on the first day. For this measurement, it's just a showcase. So this may not be, the real hardware, the most performant hardware memory bandwidth. This is just a showcase. But anyway, as you can see, this is 44 gigabyte per second for the CPU memory. And for the host and accelerator, so GPU data transfer, this is 32 gigabyte per second. This number is limited by the PCI Express bandwidth. So basically, the hardware limit here is 64 gigabyte per second. You can find this number on the slide, because this must go through PCI Express. And the very interesting one is the last one, okay? This is the memory transfer for devices, you know, inside a GPU. So basically the GPU memory data transfer. As you can see, this is already 4 terabytes per second. This is 4,700 gigabytes. So 4,700 gigabytes is 4.7 terabytes. Yeah, my goodness, my mathematics is broken. So this is 4 terabytes. This is very, very high, you know, for memory transfer. So you may have a question. I think some of you may realize this 4 terabytes per second is higher than the hardware memory bandwidth, right? The hardware GPU memory bandwidth is only 2.4 terabytes per second. But here for our measurement, we get 4.7 terabytes per second. Those two numbers do not agree with each other. So maybe just you know, a short quiz, or maybe we can think about it together. What might be the cause that now for the measurement we have even better memory bandwidth than the hardware? You know, the hardware only provided 2.4 terabytes per second, but here for the measurement we have 4.7 terabytes per second. And if we grab accelerator, you will see this. This is constantly 4.7 or 4.4 or 4.7 terabytes per second. Why we have even faster memory bandwidth than the hardware? I'm not sure. Anyone can make a guess, crazy guess, or maybe PC2 purchased a super GPU so that we have even higher bandwidth than hardware. So maybe you can think about why the measurement is higher than the hardware specification. Let's say for 1 minute or 2 minutes. Or feel free to type or turn on your microphone. It's it's not a problem. So okay, maybe I continue to explain this. So for this GPU memory bandwidth, this is the real GPU memory bandwidth, right? I mean the GPU memory bandwidth. But there is also a memory hierarchy for the GPU architecture. So besides the GPU memory bandwidth, there is also the so-called cache on GPU. And for this code, as I mentioned, this code is not a professional memory bandwidth measurement code. And it has a small size of data. If we look at the source code, the data size is small, just a couple of several megabytes, or you know, not really a very big chunk of data, so that one can ignore the so-called cache effects. In this very fast test, we use small data, and this small data may be stored or may be easily heated during the cache. So that is why we have a higher memory bandwidth than the hardware specification. If one really want to measure the GPU memory bandwidth, one need to ensure that the data set is large enough, much larger than the last level cache on GPU. And then in this way, one can, let's say, get rid of the cache effects. Otherwise, because of the cache involved for the measurement, the bandwidth reflected here is larger than the hardware specification. But anyway, as you can see, the key message I would like to deliver here is the accelerator or GPU memory bandwidth is much higher than data transfer between CPU or data transfer between CPU and the GPU. So we need to avoid unnecessary data transfer between host device and target device in order to have high memory bandwidth. So this is the performance tip we would like to share with you. And also the end of this exercises. So do you have any questions or some comments? Feel free to ask.
Perhaps I make a short comment, Xin.
Yes.
I think your explanation was very good. I like that. And I want to point out that the memory bandwidth is an important property of the hardware, of HPC hardware. And what we see here is really exceptional. This is one of the reasons these GPUs are so expensive. And we should be this is really exceptional that we can see this in such a system, and that we are able to support our users with this high performance. This is a really crucial number, and that's why I think it's really exceptional. Very nice.
Yeah, thank you very much, Matthias. Yeah, you are expert about CPU. As you can see, this measurement is crappy. Yeah, this measurement is not professional. I fully, yeah, I have to say this. This is not professional. Okay, maybe we take another, let's say, give it 20 minutes for the very last Hanzang. It's if you look at the table, it's slightly long. So I give you 20 minutes so that you can take a look at the very last Hanzang on your own and quietly, and then we can discuss the last Hanzang. I will talk at 15. My goodness, my math. 37. Yeah. So for the very last Hanzang, it's about using SAXPY to do some test on the GPU. This SAXPY stands for single precision, this scalar vector multiplication add. And this is similar to the example shown by Matthias on the first day. He was using double precision, but here it's for GPU, I'm using single precision. So first, to examine the source code in the directory. And then in the source code, we have two macros. Those two macros are used in the source code, but without definitions. So I think we can look at what are those two variables there. The first macro is the number of the GPU teams, which we have seen on the slide. and the second one is the number of the GPU thread per team. So let's look at the code. As you can see, the code is also very simple. So OpenMP header file for OpenMP offloading, this is also needed. Those two macros, the first one is for memory alignment on CPU, which is, let's say, not very critical here. And then the second one is to do this measurement repeatedly. Here, do the measurement 4 times. So, and then we have this SAXPY, let's say, a kernel or function you would like to run on the GPU. And let's move to the SAXPY kernel that you would like to do the offloading. If you look at the overall code structure, this is, let's say, almost identical like a CPU code. So basically, there's no, very particular statement or instructions for GPU. It's pretty like CPU code. And then here, you see this again, this target teams. So the GPU teams, and then map, this sharing the data between host and target device, and then distribute the teams. And then once again, parallel for, here I missed SIMD, you can also add SIMD. And then the number of the threads. So here, there are two important macros. One is the number of teams, and another one is the number of the threads per team. So here, those two macros refers to particularly for GPU. And in the morning lecture, you heard from Christian that for CUDA, you may need to specify the X threads, in the X direction, or Y threads in the Y direction, or Z, to make everything clearly like a real 3-dimensional, GPU, this 3D. For OpenMP, this is rather simple and just like normal OpenMP CPU multi-threading. So here you just specify the number of the threads, but here for GPU, you can think about it like a 1-dimensional problem. So do not overcomplicate this. And the philosophy for OpenMP GPU offloading is, just focus on the program, the science itself, not focusing on those many technical details. So here you can use this just like very similar like CPU. So here you can change the number of the teams and also change the number of the threads per team. Here you see something new, this distribute schedule static. So as you have learned on the first day, the scheduler for multi-threading on CPU. For GPU, there is also a scheduler. And here we just use the, let's say, the most standard one, the static one. For SAXPY, this will, let's say, this plays no role for the performance because this is pretty the same for the same workload for each thread. So this is the SAXPY. You can run it on GPU with different number of the teams for GPU teams and different number of the threads. And then you can create a job script This job script looks slightly complicated, but in principle, it's very simple. We define the number of teams for the GPU. Let's say you can have one team, it's not a problem. To have one team, it's not a problem. Let's say for functionality. But for performance, as you know, only one team, it's very slow. And then to do 128 teams to 256 teams and so on. Yeah, everything is possible. You can also give it some other numbers. This is totally fine. And then the number of threads per team. And then you can specify one thread per team, which is not good for performance, but functionally it's fine. And more threads per team, and so on and so forth. And then here, this is for debugging purpose or showing the result to show me the number of the teams, and then the number of the threads. And then we do the compilation and NVC compiler, and the number of the teams with the definition for number of the threads, and then C flag. This is like using GPU for OpenMP offloading. And then after compilation, we run this code, but this time, in order to avoid the so-called cache effect, we give it, let's say, a large number. Here, I just, I think this is 128 megabyte times, the size of the single precision. It's, my goodness, my math is broken, but I hope this is large enough for the benchmark. And then we run this repeatedly, and it will print out the performance. Sorry for so many debugging information, because I was struggling with this segmentation fault, but we can get rid of this very easily. Let's say this clean slurm dot out vim clean slurm. Yes, now this looks much better. So yeah, for the first one, I need to also include the number of threads information. This is n teams. Now I hope this works. This is a little bit nervous doing live coding. N teams everywhere. This let me do it forcefully using complicated syntax. This space and then delete. Now it's clear. I passed my Vim examination. So the first one has one teams, and for each team, there's only one thread. So this is very simple, very naive. And then, as you can see, this benchmark took 8 seconds. The bandwidth, the flops is very low. The benchmark, the memory bandwidth is very low. This is very low performance. And if you increase the number of the threads per team, for example, here we still have one team, but we have more threads per team, right? And then you see the wall time decreases dramatically. And as a consequence, you have higher computational power and higher memory bandwidth. And you can increase the number of the threads continuously, to have more threads per GPU team, but the performance becomes a constant. This is once again because let's say the benchmark size, and also it is somehow sooner or later bound by the PCI Express, and also bound by the total number of teams. Now let's keep increasing the total number of the teams, and as you increasing this from 1 to 128 teams, and then have this number of threads also increasing. And then you can see the wall time continue to decrease, right? You can see the in this region, the wall time continue to decrease. And then the computation power increases, and as a consequence, the memory bandwidth is also increasing. And then we can, increase to do this scan for both number of the threads as well as the number of the teams. And in the end, for example, we have number of the teams equals 512. Number of the threads per team is also 512. So as you can calculate, the total number of the GPU threads is roughly, I don't know, 100,000 or so. This is still too few, because normally we want to have millions of threads. But the trend, as you can see, is the decrease the number of the wall time, and the increase the number of the computation power, flops, as well as the increase the number of the memory bandwidth. So basically, this example shows you clearly that by using OpenMP, you can control to do some fine tuning. If you are not satisfied with the default value from the compiler, you can do some fine tuning for the number of the teams on GPU and the number of threads per team on GPU, and then to increase the performance further. Yeah, this is a showcase to do some small fine tuning, but normally the compiler is stronger enough to pick an appropriate number, for example, for threads, for team, so that you can have immediate speed up for your application. I think now you fully understand. You understand this. Yeah, this is 2 to the power of 28. You understand this, the purpose of these exercises, and through these exercises, you can clearly see the increased performance with increased the number of teams, as well as increase the number of threads per team, and then to have a better computational performance and better memory bandwidth. So this is a small showcase for you if you want to do more fine tuning. Yes, and I think this is the end for my hands-on part. The last one is an open-ended task, which is very challenging to do matrix multiplication fine-tuning on GPU. For me, privately, I can achieve 60% or something like by using OpenMP offloading, compared with respect to cuBLAS library, 60%, not 1/6, but roughly 60% of the cuBLAS library. This is already, a good sign. that you can still program at high level, but reach very high performance with OpenMP offloading. Because of the time reason, I'm not going to dive into this open-ended task, but the third task is very representative, and I hope you see the differences and also see the gradually increased performance by increasing the number of the teams and the number of the threads. So are there any urgent questions? Or don't be shy, look at me. I made a segmentation fault during the hands-on. Yeah, don't be shy, just ask questions. Yeah, I will try my best to give you an answer. Well, yeah, thanks for your question. So there is a question in the chat. I think this is an interesting and important question. So there, if there is some room to know the optimal number of the threads and groups, so the optimal one is, let's say, for me, I just let the compiler to make the decision. For one thing, this makes your code more portable, and different compilers will have their own optimal settings for this number of threads and number of the teams. So for me, as you can see on my slide, I always use the default one from the compiler. So offload this fine-tuning thing to the compiler so that to get the default one. And yes, the second question is, we deal with vector operation loops. We take care of the contiguous arrangement of the data. The OpenMP enabled compiler or the OpenMP compilant compiler will do this for you automatically on GPU. So basically, you needn't to think about too much. So just keep it as simple as possible. So based on my opinion, the compiler, especially newer compiler, it becomes rather smart. And I think different vendors, for example, NVIDIA and AMD, they also want to push in those directions to have a common standard so that everyone can program GPU easily, without too overcomplicated. Yeah, this is my impression. So no worries, just use those simple OpenMP directives and then you are completely fine. Yeah, thank you too, yeah.